The first spacewalk on the ISS was completed on 1983 by Story Musgrove and Donald Peterson. And basically, this is a big step for humanity. The ISS came out recently, and they were supposed to do routine missions. Basically, these spacewalks have symbolized the future. But an unknown fact is that the same spacesuits that they used in that 1983 spacewalk, they use now, dating the technology all the way back to the 1980s. And this can be a serious problem as the suits were made back in the 1980s and they were expected to last 15 years, yet we're still using them now. And they do serve their purpose, except due to the data technology, this can often lead to cancellations of spacewalks as it can be very dangerous. For example, the cancellation of the all-female spacewalk was due to those spacesuits. We need an update to these suits to allow for future progressions in our journey to space, and this is going to be our foundation to going to the moon, Mars, and beyond. Now these spacesuits basically act as a life support system. They're supposed to allow astronauts to go into space and not die in the process of going into this cold vacuum. These spacesuits are called extravehicular mobile units, and those are the ones that NASA uses on their ISS spacewalks. And now these spacesuits have many functions, including allowing for mobility, creating a breathable atmosphere for astronauts, controlling temperature, and protecting against particle impacts and radiation. The current spacesuits today can allow an astronaut to be in space for 6.5 to 8 hours. And it does this by the use of many layers of different types of fabric that serve different purposes. For example, it uses a Kevlar layer to protect against the micro-asteroids that may impact the suit in space. Now we're getting to the point where this technology is showing its date. And it's the fact that these spacesuits are absolutely bulky, and you can see a picture of them. You can see they seem very heavy. There's not that much mobility, which can actually be hindering towards these missions. Now, this mobility is caused due to the pressurization of the suits. So the pressurization of suits is supposed to help against two things. First off, towards protection against micro-asteroids, and these spacesuits are basically protecting those astronauts and saving their life. So that's through the pressurization. It creates this kind of hard bubble shell to protect those astronauts. And the pressurization is also helping against allowing the astronauts to actually breathe and preventing decompression sickness. So decompression sickness is caused when the nitrogen that we inhale is unable to fully dissolve in our bloodstream. So there's bubbles, and these bubbles can actually be very dangerous as it can block arterioways and may restrict blood from going to important vessels. Or these bubbles may expand and causing further injuries. Therefore, by decreasing pressure, you risk decompression sickness and fatal impact from the micro-meteoroids going all throughout space. In space, there's another obstacle posed, which involves the X-ray radiation. So while in space, there's no atmosphere that is basically deflecting off these waves of radiation that we see. So when we're directly in space, you're exposed to the gamma rays, X-rays, UV rays, all these harmful rays that can actually be very deadly or have fatal side effects. Therefore, these spacesuits, they have to protect against these electromagnetic radiation waves. Current spacesuits protect against 155 to 205 MeVs in terms of energies of electromagnetic radiation waves. This leaves minimal to no protection against X-rays or gamma radiation. which is very apparent due to our sun that emits these radiation waves. Therefore, current spacewalks have to be scheduled to look at when solar activity is when it's at its lowest. This is not ideal. So let's say when an astronaut needs to do like a quick repair on a part of the ISS, when something breaks unknowingly, they can't actually go straight out into space without risking their lives based on the radiation levels and that activity. Space poses many problems, but these are actually solvable using the new advancements in material science that we see today, specifically looking in this nanotechnology, nanomaterial realm. So to do a little bit of a debrief on what exactly nanotechnology is, it's hinted by its name that it works on the nanoscale, so think 10 to the negative 9 meters. And to just show exactly how small that is, think a single strand of your hair. So grab a piece of it, and a nanometer is basically the fraction of a width of a single strand of hair. So very tiny. And you may be wondering exactly why are we working on such a tiny scale? And that's due to the different properties that actually arise working on this nanoscale. So on a macro scale, you have one set of properties. Like with wood, you have the strength. With fabric, like textile fabric, cotton, it's more flexible, it's more bendy. And the perks of working with a nanoscale is that you get a whole new set of properties. You can get increased strength, you can get different, you can get fluorescence, different electric conductivity. There's a whole new set of properties that arise just by working in a different scale. So basically, what I want to kind of research into is utilizing carbon nanotubes embedded with bismuth oxide nanoparticles as in spacesuits as X-ray radiation protection and protection against micro-asteroid impacts. Carbon nanotubes are a type of nanotechnology, as they work in the nanotech field, as they are range from 0.5 to 100 nanometers in diameter. So these carbon nanotubes, they are credited for their strength, and that is due to the actual formation of these carbon atoms that these carbon nanotubes are made up of. Now these carbon atoms are arranged in this hexagonal pattern, also known as an aromatic ring. And basically, all these hexagonal patterns are linked together to form this lattice kind of structure, which is then rolled up into a tube-shaped molecule, forming the carbon nanotube. Now, there's different types of carbon nanotubes, and this is basically related to the fact of how many carbon nanotubes are within one carbon nanotube. And they relate to this by calling it through walls. So a single-walled carbon nanotube only has one carbon nanotube. It's only made up of one. But a multi-walled carbon nanotube is made up of multiple carbon nanotubes that are within each other. And the multi-walled carbon nanotube, although they're not as stable as a single-walled carbon nanotube, they are much more sturdy and they have much more strength. Now, to actually quantitatively look at the strength of carbon nanotubes compared to a strong material we see today like steel, a carbon nanotube is 170 times more stronger than steel. And now that's credited due to the actual size of the carbon nanotube as well as its chemical makeup. Now, to talk a little bit about the size component, I'm going to give a little bit of a brief lesson on tensile strength. So tensile strength relates to the elastic modulus, and where you're basically trying to pull part of material to see how long it can stay up. And you're trying to test a tension force. So steel and other materials, they eventually break over time because they develop microfractures that increase over time as this pulling action continues, therefore causing a split in the material. But carbon nanotubes, on the other hand, due to them being so tiny, they don't have these microscopic fractures, as they are microscopic or even tinier. Therefore, carbon nanotubes they're one single molecule. They're not joined up by crystalline grains, so they have much more strength within each other. Now, looking more at the chemical makeup, carbon nanotubes use an sp2 hybridization arrangement. And it sounds like this really big word, but basically the main takeaway from this is that these carbon molecules are joined together by double bonds. Therefore, there has this increased strength within these actual atoms that are keeping them together. Now, the radiation portion of protection for carbon nanotubes comes from the fact of both the bismuth oxide nanoparticles as well as this effect known as the Compton effect that these carbon nanotubes utilize. Now, the Compton effect basically works by scattering radiation waves. And it does this through having an incident ray. So let's say our X-ray comes in and it touches this target electron. So these target electrons come from either free electrons roaming around or loosely bounded valence electrons. And once this X-ray hits this target electron, some of the energy is absorbed and taken in the electron, and it moves in one direction, while the X-ray moves off in another course as it loses some of that energy, but its wavelength increases. Now, this is where the bismuth oxide comes in. So bismuth is a type of metal, and bismuth oxide is when the bismuth metal actually loses an electron. Now, bismuth oxide is actually very helpful towards this Compton effect, as it has many loose electrons in its valence shell, therefore increasing the probability of this Compton effect occurring. Bismuth oxide nanoparticles are also very free to move. Now, the nanoparticles basically comes from the fact that these bismuth oxide are on a nanoscale, and they're embedded within the carbon nanotube structure to basically give this carbon nanotube X-ray shielding properties. Now, the radiation shielding effect also comes from the fact that these are multi-walled carbon nanotubes. Therefore, there's multiple walls for the radiation waves to actually bounce off of and lose energy. And this process is called energy attenuation. Now, to actually create a fabric out of these carbon nanotubes, to create a layer within the spacesuits to put this carbon nanotube fabric on, we actually can create a fabric called buckypaper. So buckypaper is basically what you call a fabric made out of carbon nanotubes. And buckypaper uses a process similar to how you would make paper out of old newspapers. So basically what you do is that you place these carbon nanotubes in water and you suspend it with some type of chemical. One example is the nanosperse AQ. And this carbon nanotubes are suspended in the water, and then you place this membrane support on top of those carbon nanotubes, and this acts as a temporary support as those carbon nanotubes dry. And then once those carbon nanotubes dry, you can remove the membrane support and you're left with the freestanding paper. And this paper / fabric can then be put and used in testing. So that brings me to the part of testing of how we're actually going to see if these carbon nanotube paper, buckypaper, can actually perform in conditions. So the first initial testing on Earth is going to be looking at X-ray radiation protection, durability testing, and strength testing. First part, the strength testing, we're going to do two sets of ways. So with these micro-meteoroids all going throughout the space, they have this property. Not only when they impact, it's going to lay this force, but they also have sharp edges which may puncture into these spacesuits. So we're going to simulate of how the carbon nanotube fabric performs under this puncturing kind of force using an 18 gauge needle. And we're going to use several different forces. We're going to increment it by tens or fives, and we're going to slowly increase the pressure or the force that is applied to the buckypaper, and then we're going to record when exactly does that paper puncture. Now the other part of strength testing is that we're going to actually apply a pressure to this buckypaper to test how it performs under these sort of pressures that a micro-asteroid might provide. Now the pressure will be incrementing by 5 gigapascals, starting at 25 gigapascals and incrementing until it reaches 70 gigapascals. And if the fabric fractures before that, then the testing would stop immediately. And if not, then we would stop at 70 gigapascals. And over time, we look at how exactly does the fabric fray over time, is there any fractures or puncturing. Now for the durability testing, we're going to use sort of a dynamic testing. So we're going to basically continuously remove and put a load onto the carbon nanotube paper, the buckypaper. So we're going to look at using a 55 gigapascal pressure, and we're going to continually put this on the buckypaper on and off several times to look exactly how the carbon nanotube buckypaper reacts and how many times does it take before the actual paper kind of develops a puncture. So we're going to just be looking at what happens in this process. Is there fraying? What kind of repairs need to be possibly made over time to give a kind of sort of timeline. Now the last part comes to the X-ray simulation kind of testing. And we're going to be using a galactic cosmic ray simulator, also known as a GCR. And that basically produces these high energy ion beams to kind of simulate the effects of electromagnetic radiation. Now the radiation that we're going to observe is the effects that happen towards the buckypaper is going to be similar to, is going to fall in the same range as the X-rays and maybe hinting towards the gamma rays. So specifically, we're going to be looking at ranges of 145 EVs to 125 kilo EVs. And that's basically the range of the X-rays that we're looking for. And we're just trying to observe how exactly does this buckypaper react over time, and does it fray or any permanent damages are in place. Overall, with the embedding of bismuth oxide nanoparticles into carbon nanotubes to create a buckypaper fabric, we can create a fabric that is more durable against micro-meteoroids, as well as protects against X-ray radiation, something that previous spacesuits haven't been able to do before. And while one gap may be is that these carbon nanotubes can often be a quite expensive process, and it takes it's harder to produce a lot of carbon nanotubes in a huge quantity. But to overcome this gap over time, I potentially see this technology developing out as carbon nanotubes are becoming a big interest for many different industries. So this carbon nanotubes kind of manufacturing process, I foresee in the next few years will become easier and cheaper. Through the constant iteration of spacesuits allow us to push to the unknown. They are basically responsible for all our life functions. They're like our little kind of spacecraft for us to roam around in. And no, not like the little UFO like kind of disc thing. It's our actual suit that we can wear. Just like how one has to dress appropriately for the weather, one has to dress appropriately for the planet that they go to. We're going to need to make constant changes in our spacesuits, as each planet and celestial body brings their own set of problems. For example, with the moon and the lunar dust, that is the main reason why when astronauts came home from these lunar missions, they developed scars because the spacesuits were unable to protect them against the lunar dust that like kind of rubbed against these suits, puncturing and leaving scars. And that's also why, looking now into future missions with Artemis, they had to actually delay their mission by 1 year because the spacesuits weren't ready in time due to technological barriers, as well as the lack of funding. Spacesuits are such a vital part of this journey to the unknown, and space holds so much potential. Take the internet, for example. The internet connects us to everyone, and we wouldn't have had the internet if we wouldn't have pushed beyond our atmosphere and gone into space. Now, these spacesuits are such a critical part as they are the foundation. Spacesuits are basically the vessels that hold the most precious thing of all, life.